Hello, so today we are going to do this problem, which is part of Leetcode daily challenge, time needed to buy tickets. So let's say we have n people in a line that are queuing to buy a ticket. The 0th person, so the first person in the front of the line and the last one is on the back of the lines. Just like makes sense. Now we have an array of tickets where the number of tickets that each person wants to buy is the value in that position. And each person takes 1 second to buy a single ticket, then they have to go to the back of the line, get in the queue, and then when they reach the front, buy another ticket, right? And we get an index k, and our goal is to return the time it takes for a person at position k to finish buying all the tickets he needs. So, for example, let's say we have this and k equal to 2, so we want to know how much time it will take this person to buy a ticket. So first time this one buys a ticket, goes back to the back of the line, they have 1 remaining, this one buys, they have 2 remaining, this one buys, has 1 remaining, so that's this one. So now we have 3 seconds because each person took 1 second to buy. Then it happens again, 0, this one buys, they have 0 remaining, so they are removed from the queue because when a person does not have any more tickets to buy, they leave the line, right? This one buys, they have 1 more to buy, and then this one buys, and so we are done because we are only interested in k equal to 2. And so we are done at this point, but how many seconds did we take here? 3 as well. So overall, it took us 6. So that's the idea. Now, if we take a look here, the time constraint is very small. So the first thing you can think about, let's just do simulation, which would be very reasonable. Let me just quickly show the solution here, but this is not the optimal solution. But essentially, to simulate this, well, we just need a queue because we have a line where we pop from the front and append to the back, so we need a queue. And then every time we can put the index and the value because we want to know when k is the value at k is equal to 0. So each time we pop from the front, it takes us 1 second to buy 1 element out of this x value. And then if we buy a ticket from x, we have x minus 1 remaining. If that's equal to 0, we are done if the index is equal to k, because we are only interested in how much time it takes person at position k. So we are done in that case if position k reaches 0. But if not, if this element is the remaining for this position is still bigger than 0, we need to add it to the back, right? And so that's what we do here. And then when the queue is empty, that means position k certainly was reached 0 because otherwise we would not have popped. But this won't happen unless this happen anyway. And so at the end we return count. So that's the brute force solution. Pretty straightforward. It is O of n time because we go through the queue, and then O of n space, right? And so that's where it's not optimal. So how can we do an O of 1 constant time solution? O of 1 space, but still O of n time. Let's see how we can do that. The other thing actually, it's not just O of n time, it's O of the max, right? The minimum between the max element, right, and the element at position k, because we do this one, multiplied by n, because we do this pass, we do a pass this number of times, right? Because either this reaches 0, or actually just this, right? This is going to be the limit. So if the value at position k, let's say, is 100, then it will and the length of the array is 100, then it will take us 100 multiplied by 100, right? So it's quite expensive here. So let's see how we can do an O of 1 solution. I mean O of 1 space and then O of n time solution. Okay, so let's see how we can do that. Well, the first thing to know is, let's say we have this array, for example, right? And we have k may be equal to position 2. Okay, so these are the positions and this is the array. Okay, now what's sort of a couple of things we can note? Well, for us to reach this one, we need this one to buy a ticket, this one to buy a ticket. And then they get back to the back of the line, and now we have 2 in the front. Concretely, what does that mean? We need 3 to buy a ticket. Now we have 98 in the front, and we have 3 minus 1 in the back. And then this one needs to buy, so now we have 2 in the front, 5, 19, 2, and then this one buys a ticket, so minus 1. Now this one can buy. Okay, so once it buys, it goes to the front as well, it goes to the back, so 97, and our desired one here is 1. We have 1 remaining. And then this, we need also all of these to buy to reach this one again, right? So that's the first instinct, is that for this one for us to buy all 2 tickets, we need first the 2 in front to buy 1 ticket, and then when it's in the back, we need all of those in front of it to buy a ticket. That's the first one. The other thing, look at this value. This value is really big. It's 98. We don't need to do 98 passes to get this one to reach 0, right? In fact, when this one reaches 0, this one would be just 96, okay? So that's the insight here, is that you don't need for everyone to buy all of their tickets to be able to determine if this one is going to be equal to 0 or not, okay? But in our simulation solution, we had to actually execute the algorithm. Is there a way for us to not do that? That's the key idea, okay? Now, the insight, a way to think about that is, we need to think about how many this will need to buy for this to reach 0, and how many will these need to buy for us to get to 0. Because they are different. Why? Because for this one to be, if this value was 1, let's say if this value was 1, then these ones, we don't need them to buy anything. So they contribute 0 seconds. But we need these 2 to buy 1 each. Each of them contribute 2 seconds before this one reaches 0. So you already see the difference, right? If the value is just here 1, how much it took us? Well, for this one, it took us the time, let's call this array t, it took us the value of t2 multiplied by 2. For this one, it's the value minus 1 multiplied by the number of the elements, right? Each one contributed t2 minus 1, okay? And if you think of it intuitively, for these ones, because this one goes to the back, once it buys a ticket, we need, at most, we are going to need tk minus 1, because once we do tk minus 1, this one will reach, tk will reach 0, and we no longer need to buy tickets here, because it will just leave the line, it won't go to the back, okay? So what are a couple of things we can do? So we definitely know that for every I bigger than k, the minimum it will contribute is tk minus 1. Okay? And for I smaller than k, okay, smaller or equal, we know that at least tk, right? Because this one will go to the back each time. So at least we will need everything in front of it to buy a ticket so that we get to it, right? So we need at least tk. Okay, so what else do we need? Well, let's see another example. This example is a little bit skewed because they are bigger than the value at position 2. But what if the value here, let's say, is 2, but here it's 1, and here maybe it's 1 as well. Okay, now in this case, what happens? Well, in this case, this one buys, it reaches 0. So this one buys, it reaches 0, it leaves the queue. So now we have just 1, 2, 5, 19. This one buys, reaches 0, it goes away from the queue. So we have 2, 5, 19. Now we buy this one, we have 5, 19, 1. And then we need to buy of this one 4. So we have 19 in the front, 1, 4. And then 19 we need to buy, so we have 4, 18. And then we buy from this one, it reaches 0, we are done. So what did you notice? In the second pass, right, in the second pass for this one, we only needed these 2 to buy tickets. since these reach 0, we no longer need them to contribute any seconds, right? So what this tells you is, if these are smaller, then their value is enough. So t of I itself. So this would be t of I itself. Okay? So these basically are the seconds each of the values at each position contribute to our number of seconds. So let's say this is the number of seconds, and this is the number of seconds. Okay. I hope this aspect was clear. Now, I did demonstrate why we only need ti if it's smaller, but let's see why we only need ti if it's smaller for this one. But it's the same argument, right? Let's take an example here. Let's say these ones were bigger. Let's actually just take another one. So let's say our array here is maybe 4, 5, and our position that we need to get to 0 is 2. But here we have only 1, okay? Now what happens? Well, let's see. So first this one needs to buy. So now we have 5 in front, 2, 1, 1, 3. Then this one buys. We have 2, 1, 1, 3, 4. Now this one gets to 1. And we have 3 and 4. Now this one goes to the back, right? Now this one buys. It's 0, so we pop it off. So we have 3, 4, 1. And now this one buys, so we have only 3, 4, 1. So you already notice now, we only have these 2 to wait for. We no longer need to wait for these 2, right? So this one needs to only, for the next pass, it only needs to wait for these 2. It no longer needs to wait for these ones because they are out of the queue. And so that's why we also have ti in the min here. And now this is a lot straightforward because we only need to do for loop, and for each pass we know how many seconds we need to contribute, right? And so let's implement this solution. Okay, so let's implement the solution we just saw in the overview. So we don't need this anymore. We just need to do a loop. We just need to go through the tickets. And what we said is we have 2 cases. We have, let's call this seconds. We have if I is bigger than k, and if I is smaller or equal to k. Now for the front, we said we only need to contribute tk, right? Basically the value of at the desired position, or if the ones in front are smaller, then we only need that because after that they will be out of the queue. So this would need to be plus. For the ones after k, it's pretty similar, except here we need -1 because for the first pass, the value at position k doesn't need to wait for the ones at behind it, right? And that's pretty much it. Can run this. You can submit, and this passes. Now, in terms of time complexity, you can see this is straightforward of in time, and it's of 1 space because we're not using extra space, so it's a lot more optimal. Yeah, so that's pretty much it for this solution. Thanks for watching, and see you on the next one. Bye.